My first question is, does anybody still want to copy files from this bigger SSD here? If it's finished, okay, good. Right. I wanted to start today a bit light with what I brought from my home. And so we will have a look a bit at the flow. First question, does it turn this way or does it turn that way? Can I ask for your hand sign? Who thinks it turns this way? Okay, who thinks it turns this way? Okay, right. If you imagine that where the camera is the sun, and we have the Philippines here, the sun rises in the east. That means we are turning this way towards the sun. So that is the way the Earth is rotating. Right. My next question to you is: we are using a lot of Earth observation satellites. For this, if you take this globe, how high above the surface of the globe are the satellites? Like this. So, can somebody show me with your hand or fingers what you think how high it is? Okay. What's your guess? How high above the Earth are the Earth observation satellites we are dealing with? Yeah. Okay. Okay. Yeah. Good. Good. Is it typing? Sorry. Okay. 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 You probably remember that most of the satellites we are dealing with are 500 to 1,000 kilometers above the Earth. We were right. The lower ones are around 500 kilometers. If you take the Philippines and 500 kilometers in the Philippines, this is about the length of the width of my small finger. So this is how high the satellites are flying. So most of you were far too high. So the satellites are actually quite close. And the International Space Station, for example, is 440 kilometers above the Earth. So that is, you really have to look carefully to see that it's above the surface at all. So, but we have also some other Earth observation satellites which are geostationary. What do you think? How high are they above the 700 kilometers? Or who has an idea how high the geostationary satellites are? That means the ones that are turning around. That means the ones that are turning around the Earth in 24 hours. That means the Earth is turning around in 24 hours. So the satellite flies exactly the same speed. But they are higher. No idea? Okay, about 35,000 kilometers. So you cannot see any real details anymore from that height. That should be something like this distance from the Earth, where the geostationary satellites are. So some weather observation satellites are like that. Because, they don't want to see the details of every cloud. They want to see the structures of clouds. So so that is then fine then you have a big area that you can observe with a satellite, but you don't observe the small details. Right. If I have this, how far is the moon away? About the end of this boat, that would be a moon. So something like that in this order of magnitude. All right. What are the trajectories of the satellites we are dealing with? Are they spiraling around the Earth? Are they going around the equator all the time? Or how are they flying? they go around the Earth, but in what pattern? Are they just circulating around the equator? Are they going from pole to pole? Are they doing spirals? Any other here pole to pole? Any other object? Yeah, that's correct. They are doing that. So they are going around the pole, and basically the Earth is circulating under them. They are kind of constantly going like that, and the Earth is going like that, like this. And so they don't have to do much. So every point of Earth will be covered because they are doing controlled their rounds. There are also the satellites we are dealing with are doing that, but there are also others. But the ones we are dealing with are doing that. And it also means that, they have a certain spot width. If you are closer to the pole, they are covering the same area more often. If it's at the equator, they don't cover the area so often. But I'm today introducing one example of a more, say, complex utilization of Earth observation data, because we use a lot of different Earth observation data for what I'm introducing today, and they come from different satellites with different types of processing, but the end is something that is mostly based on hazards. So it's basically saying how dangerous is a certain spot on Earth, and as an application, that means how suitable is it for a certain type of asset. And the asset that I'm dealing with today, as an example, is a house, a residential house, a normal single detached residential house, not very sturdy. Not absolutely strongly engineered, but also not a makeshift type of shed or hut. So it's a type of average house. You have about 22 million houses like that in the Philippines, so it's a quite common asset. And what I'm using here is a type of average. So if you look at an individual house, it's probably stronger or less strong than the average type of house. So, and then it is also more susceptible to damages or less susceptible to damages, depending on the characteristics of the house. I'm using a residential house, but you can, for example, also do that for crops. So, and for any other asset, for that matter, but crops would be something that's, of course, economically interesting. And you will, of course, see that crops have very different vulnerabilities from buildings. Some crops are very susceptible to flooding and can be killed by a flood, while, say, for example, coconuts are not very susceptible to flooding. So it depends a lot on the type of crop. And yeah, compared to buildings, for example, collapse from earthquakes, plants are normally not really affected by earthquakes. All right, so what do we, I think I gave you a hint of what suitability maps are like. And we go through different steps, and later we also do some exercises, but I start with some more theoretical introduction to the concept of suitability maps. Okay, I will explain a bit more about the concept, and then we go through these through the 6 different hazards that are important in the Philippines for buildings. For example, I didn't include drought. So for buildings, drought is not interesting because it does not affect buildings. But if you go into agriculture, of course, you would include the hazard drought, so as a factor. But then I introduce the concept of average annual losses, AAL, and that it's important that your a building is in a safe place, but there are also other things which are important. For example, how close is it to a road, to a school, to a hospital, whatever. I have here two examples. One is population proximity and the other is road proximity. Population proximity is especially interesting if you want to have a business that is relying on walk-in customers or so. If you want to have a shop, you want to know how many people are living around that shop. So, and if you have, for example, a plan to build a chemical factory, which is dangerous, you want to be away from many people, so you look for a place which is not so densely populated. Okay, and then we have also exercises. Okay, let's start. So to visualize that it's not that easy to simply look at hazard maps. I put here an example that's actually from Nathan Abuyok, where you see on the right, you see the sea. Then you have land, relatively flat land, which is green. Then you have a river mouth, and you have some mountains. You can see them here. And then I overlaid that with a hazard map. That is the ground shaking hazard map or earthquake hazard map. So you see that from the map I have here, there are certain places where the earthquake hazard is stronger, and in other places it is not so strong. It's expressed here in peak ground acceleration. That means how fast the acceleration of the ground is during an earthquake. So in centimeters per second squared. I would like to point out that this is a bit of simplification, because if you look at earthquake hazard maps, you see very often that they come with different return periods. So 1 in 20 years, say, return period, 1 in 100, 1 in 1000, and so on. So you have normally, if you look at a bit more in detail at the stuff, you will see that it's not only one earthquake hazard map, but a set of earthquake hazard maps. So this is a bit of a simplification here. Okay, next I overlaid it with storm. It's not very easily visible, I think, on this projection, but you can see here some areas where you have certain wind speeds. You have here the wind speed that you expect. So, it's not. I think the graph is not perfect here. Next is I put on storm surge. So you see in this area here at the coast, you have storm surge areas. But here in the mountains, no storm surge. Okay. Next, I put river floods. That is already a little bit complicated, but at least nicely visible. So there's an area here which is strongly affected by, or can be strongly affected by river floods. And this area here is very flat. So naturally, this is a flat-prone area. So, and of course, no flats in the mountains. No flats. Okay. Then I put tsunami. So we have an additional layer here along the coast. So here, tsunami height up to 5 meters. So you see some areas here. And then landslide. Landslides are only here. Because here, the flat-prone areas, you don't have landslides, but here in the mountains, you have landslides. Okay, so this is 6 layers, and visually, it's getting a bit confusing. So if you, and it's a simplification, if you really take all the available layers, you end up with 25 to 30 layers. So depending on what hazards you select. And then, of course, if you want to know, so how say, I take a certain spot here, how safe is a house there? So that if you have 25 layers to look at, it gives you a little bit of a headache, I guess. So so there is a need to simplify that and to develop a method with that you can put this all together into one map in the end. Okay, and that is exactly the suitability map concept that I'm introducing now. So this is just why we do that, because it's too complicated to work with 25 layers. There is no, yeah, so in this type of map, you also don't have a ranking. So there might be actually hazards which are not important for your building or for another hazard. So you have no ranking there. So that is why we have to have a method to see which hazard is more important than another one. And then the basic idea for the whole thing is that all hazards are in their characteristics very different. But they have one thing in common: they are causing damage on buildings or other assets which can be quantified. So you can have, say, 10% of the value of a building damage from floods or from high wind speeds. The characteristics of the damage will look different, but 10% is 10%. So if the roof has flown away, and that is maybe 10% of the value, or if the ground floor is devastated by a flood, that is probably also 10%. It's both the same. So what we are doing in this exercise is we calculate in pesos or in percentage of building value how much damage does a certain hazard event cause. And then you can compare it. And you can put it together. So you can add up all the different damages and say this is what I'm expecting as damage. And the way that is normally done, the convenience, how it's done is to look at 1 year as a reference period. So how much damage do you expect in a year? So, and that is then called average annual loss. So that might be very small, but if it's of course that is an average. In other words, it doesn't mean every year you will have exactly this type of damage. You can have for a long period no damage at all, and then suddenly you have a big event and you have a big type of loss or damage in your asset. Okay, let's have a look at that, how this theoretically works, so that we have a better understanding of it. Yeah, so we are using two factors of hazards. That is the probability, how often is it expected to happen, and the second one is how intense is it, how strong is it, and so on. So that are the two factors we are using. We are using it here for residential buildings, but the hazards are the same for any other type of asset. Only the impact on the asset is very different depending on the respective asset. Okay, and I already said that. Quantitative way, expected damage cost and percentage of value per year. Or you can also translate it to Philippine pesos. If your asset is 1 million pesos, you can put it into pesos. If your house is 10 million pesos, of course, the expected damage then is higher. Okay, that can be used for land use planning. So you can have a look how dangerous are the places, and of course, especially for, say, essential infrastructure like hospitals, police stations, power plants, and so on, you would try to look for the very safest place that you can find. But when for others, you probably do a bit of compromise. But you can also, when you use other areas, you can look at the composition of the hazards. And if there is a certain hazard, you can probably see that for this particular hazard, the buildings there should be especially strong. So if there's high wind speeds, you would have to see that the the only hazard is high wind speeds, and you have to see that the roofs of the high buildings are well tight. Okay. But it can also be used for other purposes, like, for example, insurance purposes. So if an insurance company is interested to know what is the expected damage, they probably could have a look at a map like that and say your house is in a safe place, so you don't have to pay so much for the insurance, or your house is in a dangerous place and you have to pay more. Now a little bit the theoretical background to that. You, of course, have heard the name, these three terms: hazard, vulnerability, and risk. And people not working in these fields are sometimes confusing these terms a little bit, but for people working in the field, these terms are very clearly defined. So there is also a kind of official definition list by UNDRR, the United Nations Disaster Risk Reduction Office, where you can find the definitions of these different terms. So hazard is a potential dangerous event, natural in our case, where the impact could result in damages and losses. Vulnerability is the physical characteristics of an asset to be susceptible to the impact of the hazard event. And together that gives risk. So there is, if there is a hazard, but no asset, you cannot have a risk. So there are places on Earth where some islands in the Pacific with a big volcano, but there is no asset that is interesting to humans, so there is no risk from the human perspective, at least. For the fishes around in the ocean, probably yes, but from the human perspective, there's no risk. And the other way around, for example, I come from Berlin. The buildings in Berlin are not particularly earthquake-proof, but we have almost zero earthquake risk, earthquake hazard. So doesn't matter that the buildings in Berlin are not very earthquake resistant, because we don't have the hazard. So we don't have a risk of earthquake damages. Okay, but in the Philippines, unfortunately, you have both in most of the places. So you have a hazard and you have vulnerabilities, of course. So, but by the way, which places in the Philippines are the safest? Palawan. The south of Palawan? Okay, very. In terms of natural hazards. I mean, human-induced is maybe a different story, but Tawi-Tawi and the south of Palawan and so on, from the natural hazard point of view, are the safest places in the Philippines. They are actually really a relatively low danger level. But here, Visayas, Luzon, it's quite significant hazard levels. But the north of Palawan is not so safe.
But the central not including the city is not roads because of anthropogenic economy.
Yeah, okay. So I don't want to dispute that. So, but relatively speaking, really south of Palawan and this Tawi-Tawi and so on, this area, Zulu, is relatively safe. So if you want to build your next house, probably you feature that in your considerations. Okay. Yeah, I mean, of course, we have places like Cantantuanes and so on where you only have a high risk. So, all right, here I quantify these terms. Hazard, I mentioned already, probability and severity. And vulnerability, so the physical susceptibility and also the value is important. So that we factor in. And that what you then have as a risk is a value over time. In other words, the average annual loss that we are using. Okay, if you are familiar with curves, that is how these things look like in graphic display curves. So the hazard distribution is like this. There is a relatively frequent hazards with low intensity. So say wind, there's always a bit of wind, but it's not damaging yet. And if you go higher with the occurrence is less. So it's not happening very often. So if high wind speeds are rare, and then they are damaging, and the low. So all hazards have basically this type of characteristics. And building vulnerability looks like this. So it is a sigmoidal curve, which starts with a low hazard. Nothing is happening. You can, again, for example, take wind. So if you have a bit of wind on your house, it's not affected. You don't have any damages. So we are here in this area. And then when the wind speed increases, you have a sudden increase in damages. And the reason for this is that a simple building has 4 walls and a roof. If the damages start, the rest of the structural integrity of the building is compromised. That means if the roof is blown away, the rest of the house is open, and the further damages and destruction can go on very quickly. So if, for example, if one wall falls, the whole building structure is unstable, and the rest of the building will easily collapse too. So that is this phase here, where you have quickly increasing damages. And if you have not much left of your building, additional wind speeds or other hazards don't cause much additional damages anymore. So that is this explanation is why the damages are not linear. So and also not this type of logarithmic type of curve. So it's this sigmoidal type of curve. And then if you look at the data, you will see that mostly the vulnerability data, they will follow normally this type of pattern. If you put the two together, you get a curve like this. That means most economically speaking, most damages are caused by medium events, medium strength hazard events, not the very, very rare, very strong events, and not the very frequent, very small type of events, but the ones in the middle. So that is economically what is causing most damages. For practical reasons, this is normally put into categories. So, say, for example, 5 hazard categories. So, from a low, very frequent, low severity 1, and you have these categories, for example, for earthquakes, your earthquake intensities, you have wind speed categories, and so on. So, for practical reasons, that is done. And so, and then you also see here in the hazard, in the vulnerability. So, in this example here, the category 1 is causing only 15% damages, and category 2 already 75, and then it goes slowly up to 100. Okay, so what type of building do I talk about? This is a Filipino houses. At the one side I have in mind here is something like this, like this, like this. So not very strong concrete buildings, but also not huts made only of, let's say, light materials or so. But I don't have specifics for that. It's just an average of a building. But you see also in the literature that people try to categorize this and so on. And they also don't have say it has to be exactly the wall size is this, or you cannot compare it that well. So every house is a little bit different. So it's, but basically this type of house is what I'm dealing with here. By the way, you can interrupt me if you want to ask questions, and I will try to answer. Right. Now I want to go through the 6 hazards where the Earth observation data come in. So up to now it was just a theoretical concept, but not. But indirectly, almost all the hazards are using Earth observation data, and one type of data that is basically everywhere used is a digital elevation model. And the digital elevation models we are using actually come all from satellites. So at least, I mean, you can also use the topographic maps of Pakasa, but the vertical resolution is too low normally for the purposes for us. So if you have, say, a line for altitude for every 5 meters for a flood, that is too much. So it's not good. So if you take a satellite-derived digital elevation model, you have most likely a better vertical resolution of the landscape, and then you can calculate where floods, storm surges, or tsunamis are, for example. But with 5 meters, that is not working. Okay, so for example, here we have storm surge. That is a probabilistic storm surge hazard map, saying how high the expected water height is. And you see here up to 5-6 meters in some areas. I don't exactly know whether, or for 5 meters, some here on this coast. And we talked about south of Palawan and the Zulu archipelago. So you see no storm surges there. And I mean, we all know the typical path of the typhoons. They come from the southeast and they go to the northwest, basically. So this way. And then storm surge, of course, is connected to typhoon. So only if there is a typhoon, you can have a storm surge. Right. So that is an example. Then I go a little bit into more details with windstorm. I have here a cyclone hazard map with 50 years return period. So you see that I'm using here the internationally mostly used categories, which is a Saffir-Simpson scale, here, this one. And here you see the kilometers per hour. So a tropical storm is from 63 to 117 kilometers per hour. A not so very well built building will already have some damages with 100 kilometers per hour or so. And with more than 117 kilometers per hour, you will have damages with most buildings. And if you have this type of wind speeds, which is what Yolanda had even a bit more than that, then you will probably see damages in all types of buildings. So, and many buildings will be simply completely gone for that type of speeds. Okay, so you see that in a 50-year return period, some parts of the Philippines are statistically expecting this type of wind speeds, while here 4 is this area, so part of the Visayas and a good part of Luzon, then central Visayas and so on here 3, and it goes down to just tropical storm here in the south. Right, and that is just 50 years return period. So of course you can have higher wind speeds with longer return periods. But the map I showed you before is a regional map. It does not show you very local wind speeds. Local wind speeds are also depending a lot on topography. That means on ridges of mountains, mountain tops, you have higher wind speeds than in the valleys. That can be quite a difference. You have also other factors, the wind direction. So if the wind is coming from the east or southeast, of course, if the side of a mountain that is more on the northwest is more protected and experiences less wind speeds. Another factor is land cover. So if you have, say, forest or so, or dense urban areas, you have more resistance on the ground. And so if you have even the wind speed that you're expecting is reduced compared to open areas. So what I did, and what Pakasa also did once, is take the regional wind speed and downscale it to 30 meters here. I did here, and then I multiply the regional wind speed with three different factors: one for direction, one for topography, and one for surface roughness. And you have different Earth observation data going into this. The direction of cyclones is basically coming from from weather satellites. So you where the tracks of typhoons. Then you have the FATEM is digital elevation model that is done by Copernicus. That is called forest and building reduced digital elevation. Correct? Forest adjusted and building. BB is for building. So basically they I maybe one side word about digital elevation models. Or did you explain that already? Yeah. Okay. So yeah. Right. The satellites normally don't see the ground; they see the surface of what is there. That could be buildings, that could be vegetation, and so on. So, but sometimes we are not interested in how high the buildings are. We are interested in how high the ground actually is. So, if we want to do a flood model, the floods can go into the building in the ground floor. But if you take the raw data from the satellite, it will tell you there is actually a high mountain. It's a building. So there are methods to remove this from the raw data, and then we get something which is digital, say, land model or ground model, and the other one is called surface model. And in this case, they said they removed the forest and the buildings by some algorithms. And so basically, it is a model of the Earth itself. So and so I use this, but it is the data are coming completely from the satellite for the topography and also for the wind direction. So and then land cover. I took data from Filter and some from Copernicus. That is for the roughness. So there are tables where you can see how rough is forest, how rough is bushes, how rough is buildings, and so on. And I took one of these tables and calculated the surface roughness. So, and then in the end, you get local wind speed. And let's have a look at that. Just to get the concept how that is done. This thingy here indicates the local wind speed. Near the ground, the wind speed is relatively low. The higher you go, the higher the wind speed goes, and then at a certain height, it doesn't change anymore. But if you have a mountain top, the wind speed is higher. That means here you see starting from the ground, you already have a higher one. And here, if it's protected by this hill, then you have a lower wind speed, local wind speed. So that's just the concept on how this is the topography multiplier is. Right, the direction multiplier. So you see here the tracks of the typhoons in the Philippines, the historical ones. Very little here. in the very south, and a lot here. And you see that the wind direction is changing a little bit. So here it is more east-west, and here the higher you go, the more steep the track is. So I divided the country into 3 zones, where the wind comes from 90 degrees, 110 degrees, 112, 130 degrees. And then you have also of experience a multiplier. So the factor is 80% shading on the other side of the hill. So you can use this type of formula set in GIS to calculate the wind speed. Then the roughness multiplier. I took the land cover map from Filza, but unfortunately the Filza map has some gaps. That is here in black. Some holes. The black areas here is not a special land cover, it is simply no data. So, and I replaced the data with ESA land cover, so only the holes. So I only, in the holes, I took the data from ESA. So, yeah, only for the no data area of Filza. So I tried, but all the data come from satellites. So the Filza uses satellites for that, and ESA uses satellites for that. So I think you had the lecture about land cover. Probably the peculiarity that every institution that is doing land cover maps has their own categories. So you have a little bit of a problem to consolidate or compare to land cover maps. So I tried to do it, but of course it does not completely fit. So I tried to find out different land cover maps for the Philippines, and I think I found 18 or 19 sources where the whole Philippines are covered. And every one of them use their own categories, so you cannot, and their own methods of doing it. So you cannot really compare any of those. It's really a bit of a headache. So if your office is interested in leaving a landmark, you can use your own categorization and your own land cover map. So you will add one more. Okay, anyway, so that was land cover. Here is an example for the land cover, the roughness multiplier. So city buildings means that the wind speed is only 86% compared to the open area and so on. And if you have open area down here, desert or and so on, sandy beaches, it is basically 1. So, and the other factor. So it's many of them is not very much. So, okay, then let's have a look at the result. I would like to start with, let's cut the drawings. This is the topographic map of Catanduanes. So you see that they have some flat areas here, and they have some mountain ranges. And then if you go to the wind speeds, you will see that the wind speed on the eastern side is higher than on the western side of a mountain range. So you see here a small mountain range, this one here. And on the eastern side of it, you have higher wind speeds than on the western side. And that is here for 250 years return period, so much higher wind speeds in general. But the pattern stays the same. I'm not sure you can see it very well. This is Cebu City. You see here, this is Mactan. Here is the airport. And here is the city center where we are. And then we have the mountains behind Cebu City. And you can see that on the eastern side, that's actually a bit turned. I can move it like this. So you see in the valleys, you have relatively low wind speeds. And now we are looking from the east, you see high wind speeds here, especially on the top of the mountains. And so I think it stops by itself, I think. Or does it continue rotating? Okay. So you see here relatively uniform type of wind speeds in the urban area of Cebu. But here, where tops is and so on, you can have very high wind speeds. But in the valleys again, the here relatively low wind speeds. So that is a way we use quite a bit of satellite data, but the way to process them is a bit, say, complicated or so, but cumbersome. But in the end, we couldn't have done this without the satellite data. So we needed all that to do this. I have here a table with tsunami building damages, which I used. I looked around a bit, but maybe Feebox has some tables for that. I'm not quite aware. I actually think this one is a bit too high. So if you see here, the lowest water height is 10 centimeters to half a meter, and they already have 32% damages to normal buildings, which I find a bit too high. So that is knee high. And knee high is already concerned. I'm not sure. But this is actually the result of the biggest study ever done on damages from the tsunamis, which is from the 2011 tsunami in Japan. Japan is a very developed country, so they had a lot of, say, scientific power and effort in analyzing what happened during this tsunami. So they surveyed hundreds of thousands of buildings and what type of damages they sustained from the tsunami. So it's a very big wealth of data that we have there. And I took that. And also, Japanese houses are not necessarily very stable. They have also quite a lot of wooden houses. So, okay, so that is the table I used, but I'm a bit critical of it. Other landslides. You already had a session on identification of possible landslide sites. And that is here another one. I did that here. So there are landslide scars in an area in the mountains of northern Luzon. And you can also have a bigger area and identify all the landslides. What you can do is to also try to establish how big. You can also try to measure the size of landslides here. So from the satellite images, so you can. Typically, landslides are not very big, so they are say an average maybe 1,000 or 10,000 square meters. But not much bigger than that. So the typical landslide at least. Okay, so that is a selection of landslides from that area there, identified with satellites. And again, it would be actually difficult to identify the landslides with other methods. Of course you can, but you can go there. But almost all this area where the landslides happened that are identified here are in remote areas. There's no road, there's no settlement, there's no agriculture. That's in the middle of a forest or so, where you can go there, of course, fly there with a drone or so, but it's quite far. Weather might not be good, and so on. So it would be quite an effort to try to do that from ground-based with ground-based methods. If the landslide happens along a road, which is of course typical when the road is new, after first heavy rains, you have normally landslides. Then it's easy to measure it from the ground. But these landslides here all happened in remote places, where it would be really difficult to find them by going there. All right. So. I don't want to go into the details of that. You can calculate the size of landslides, how often they are happening. I did some calculations with data from NOAA, the project of the UP of Mahalakmai. I guess you are familiar with that. right? So he also did some data on landslides. So he, or the project, hazard area, according to NOAA, in square kilometers, in three different danger categories of NOAA. 17,000 square kilometers one, and category two, a bit more dangerous, 56,000 and 61,000, which is a bit less than half of the country. 300,000 square kilometers is the size of the Philippines. If you all put this together, you can get type of ridiculously low probabilities of landslides. So landslides are simply the ones that are observed are very small. And that means the area affected is relatively, the chances that an area is really subject to landslide statistically for the whole landslide prone area is low. But if you really want to know how dangerous it is, you would have to go with a geologist to the respective area and do an on-the-ground assessment. So this is very, desktop type of analysis, which is probably, I think, underrepresenting the danger. We have flood hazard maps from MGB, but they are kind of qualitative, so not probabilistic, so not giving any return periods, and that is not very helpful, so I couldn't use them. What I used is also, again, Project NOAA data. The Project NOAA data are, as far as I can see, very good, but they are not covering much of the country. So, for example, this is the Agusan area here in Mindanao, and the white area is where NOAA didn't do anything. They didn't do, and this one here is where NOAA did their calculations, their flood models. But Agusan River is really a big river and important. So I took data from another source for flood prone areas from the JRC, the Joint Research Center of the European Union. They are not as good, as detailed, and so on as the NOAA data, but better than nothing. So, and one of the big data gaps I see in the country is to close the gaps in flood hazard mapping. So also here, for example, in Cebu City, there is a flood from NOAA flood hazard maps for Talisay, for the Mananga River, and also for Kotkot River, so Compostela and the little one, but there is none for the Butuan River. So that is so that would have been, of course, helpful to have flood hazard maps which are reliable for these areas, but unfortunately, at least I'm not aware of a reliable flood hazard map or set of flood hazard maps for the Butuano River. Okay, earthquakes. You find quite a lot of earthquake hazard maps, and some are from PREWOX, but also many other institutions in the world produce their earthquake hazard maps. I don't know how to say it politely, but sometimes not reflect the reality so very well. So if you looked, for example, I looked at 5 or 6 different earthquake hazard maps after the Bogo earthquake, and it's a very safe area. So on the PREWOX maps and all the other maps that I consulted, it looked like this is not an area where you expect a strong earthquake. In 2013, we had a strong earthquake in Bohol. And the fault line, or the earthquake, the center where the earthquake was strongest, but earthquakes are not really. You see epicenter, which is normally displayed as a point, but it's not a point. So it's actually a bigger area. So and the area that was actually shaking is, according to USGS, United States Geological Survey, around this area. So you saw about this. And this is the earthquake hazard map of PREWOX. So red means high probability, high earthquake hazard. This area here means low earthquake hazard or lower. So yeah, it's. I think it's self-explanatory. But I don't want to. I don't want to blame Fevox. The others also get it wrong. So it's not that Fevox is wrong and all the others are correct. So I'm not an earthquake scientist, but as a user of earthquake hazard maps, I'm a bit wondering. Yeah, of course, it was very. I went there myself. I saw it, so it was very visible. You saw what you saw suddenly 1 meter. The one side of the ground was 1 meter higher than the other side of the ground. So it was very visible in some places where the fault line is. Some fault lines, and the one in Bogo, now with the earthquake and the aftershocks, you can identify the fault lines there. But before, this whole area was regarded to be no fault lines or whatever. I don't know exactly. So I have a little bit of issue with earthquake hazard maps, but what can you do? So, for example, here the area around Cebu, southern Cebu, Bohol, is a relatively strong earthquake area. Most earthquake hazard maps identify the Philippine Trench, which is here, as one of the major sources of earthquakes. So that's here, and then you have also the Central Philippine fault line, which goes here. That is also the Central Philippines fault line right now is moving smoothly. That means the tensions are not building up much, so you don't expect a very big earthquake there right now. Not very big, but some earthquakes are happening also in later and so on. But if you know where it is, you can, for example, later I know one point where it is. You see, if you look at the road and you look at along the road, you see that the road is like this. So suddenly something like this amount, the road makes a jump. So you see there is a fault line. So if you don't pay attention to it, you think maybe it's just a fault in the construction of the road, but it's really the road was built in one, but one half of the road is one side of the road is moving, and the other one is moving the other direction, which is in a way a good sign. All right, let's continue a little bit because we are approaching the first exercise, so it was already a little bit longish introduction. Okay, just a little bit of different sources for average annual loss. So I'm not the only one using that. So here is, for example, from UNEP, an estimate for the whole Philippines, the average annual losses for expressed in million US dollars. So not for a particular asset, but for the whole damages that in the country are sustained in the country. So according to UNEP, the tropical cyclone and earthquake are almost the same. So both about $2 billion per year, followed by flood with 1.3 or $1.4 billion per year. And then tsunami, landslide, and other hazards are not very significant, according to this UNEP statistics. And here by affected sectors, so buildings are affected by earthquakes and floods, not much by landslides, and so on. You can have a look here. Cyclones are affecting oil and gas infrastructure and so on. So, according to so this one, if you add this up here, the expected annual loss is about $7 billion per year. World Bank expects about $4 billion per year. ADPC is $8 billion per year. Okay, so but what we are doing is the per asset and for a single building here, not for the whole country, the amount of expected AL. Okay, so what we are doing is for the different return periods we are calculating we are taking from the statistics, from the map and so on, the expected severity of the hazard, and then from the vulnerability table or vulnerability curve, the expected damages. And so you have that, for example, for 4 different hazards here, 4 different return periods for one hazard, storm. So you calculate for each of them the respective annual losses. And then you have this data, and you do basically the same with the other hazards. And then in the end, you have one total hazard. There is an assumption behind that to simplify things, that all hazards come alone, which is not realistic, of course. We know that many hazards come at the same time, and then the damages are probably compounding. So they are not, say, mathematically simply adding up, but they are increasing more than just adding the risk from one and the other hazard. To factor that in a quantitative way is very difficult, and I did not attempt to do that. One word about how to calculate the average annual losses for a hazard. You start with the longest return period, which gives the most severe hazard. So, for example, here it's 200 years return period. There's a certain amount of expected damage for that, because there's a certain wind speed associated with this 200 years return period. And that is the first data you have. To arrive at the average annual loss, you have to divide the result by 200. So because this happens only once in 200 years, so if you want to have the average annual loss, then you divide this by 200. And then the next thing you do is you go for the 100 years return period. The data we get are not, say, simple probabilities, but exceedance probability. That means the value you have for, say, 100 years return period is a minimum. That means say, it's a wind speed of, say, 150 kilometers per hour. It can be more than 150 kilometers per hour, but it's kind of guaranteed to have 150 kilometers per hour in 100 years. If you have 2 of these periods after each other, also the 200 years return period will be included. So mathematically, what we have to do is we have to reduce the damages from the 100 years return period by half, because half of it is already included before in the 200 years return period. It's a little bit tricky to understand, probably, but that is the way to do it, because otherwise you would have, you would simply divide your return periods into more and more categories, and you would have more and more damages, but you don't have more damages because of more categories. So if you would start, say you have a return period of 199 years, 198 years, and so on, and you calculate always the damages and add them up, you would end up with astronomical high damages, which you cannot do. So you have to reduce the calculated damages by the higher damages from the longer return periods. Okay. So, and for example, for a 10-year return period, you have to, the calculated damages have to be divided by 10 to have the annual damages. Okay.